Hi, this is Gary Rubenstein, and in this video I'm going to show you an ingenious proof by Archimedes about finding the area of what's called a parabolic segment. By this it means we have a parabola, you can see on the screen, and I have this line segment AC, and I join AC and I shade in this area here. And depending on where A is and C is, that area can be different things. Also, the parabola could have a different sort of so-called A value, skinnier or wider. Now, he's not going to get a numerical value for the area of this. When they say quadrature of the parabola or of the parabolic segment, they mean finding an equivalent area, which is a polygon, and they have methods back then for creating a square that has the same area as a given polygon. So this is sort of the goal. See that square over here? And it says here the area of the parabolic segment is 10.12, and so is the square. When I move this thing around, you see that both things change. Now Archimedes does this proof by relating the parabolic segment to this red triangle. Now the way that triangle is formed, point D is the midpoint of AC. And then if you go sort of, this point B here is real important. It has to be on the line parallel to the parabola's axis of symmetry. So B, it can't just be any third point on the parabola, third vertex for the triangle, but it has to specifically be the one that's sort of on the line parallel to the axis of symmetry. And if you make that triangle ABC, Archimedes shows in the proof that the area of the parabolic segment will be 4/3 times the area of specifically of that red triangle. Now Archimedes actually does this proof twice, two different ways that we know of, and one is in a treatise called the Quadrature of the Parabola. But this one comes from a different treatise, which is known as the Method. And in this one, he says that this is sort of the way he figured out the formula in the first place. So I'm going to take you through the sort of lesser known proof from the Method that the area of the parabolic segment must be 4/3 times the area of this unusual red triangle. Now, in order to understand this proof, there are four sort of prerequisite theorems from geometry. One that's pretty well known even today, and then the other three are sort of less known, but they're all really important towards understanding the proof I'm going to show you. And the first one is, here I have a triangle, and if I make the midpoints of all three sides and draw the so-called three medians, they all meet at this point, G. That point is called the centroid of the triangle. And two things to know about that. One is that that point will be the center of gravity. So if you were to balance this triangle, like put a pencil through a cardboard cutout of a triangle at the centroid, it would balance nicely. So that's the center of gravity. And another property is that the centroid is cuts the median itself at the 1/3 point. So you see here it says CD is 24.6 and GD is 8.2. Well, the ratio between those is 3. And as I move the points around here, you can see that that ratio stays the same. So that's going to be important also. One, G is the center of gravity, and that GD is 1/3 the length of DC. The second geometrical thing you have to understand is what's known as the law of the lever. And the idea is this: if I have this fulcrum and I have these two objects that have the exact same weight, well, they will balance each other if their distance from the fulcrum is equal. And if the objects are not the same weight, well, then they won't balance if they are the same distance from the fulcrum. However, if the fulcrum is not in the center, the two things can still balance, but the sort of heavier one, or I should say the lighter one, is further away from the fulcrum, and we can make it so that they still balance, even though the things aren't equal, because the fulcrum has to be closer to the heavier thing. And that's called the law of the lever. But more specifically, there is a way to tell when two things, under what conditions will two things balance. And here you can see that in these circles, now circles don't have weight specifically because they're two-dimensional, but if they did have weight, that weight would be their area. So here the area of the red is 13.5 and the area of the green is 36.42, and the red is further away from the fulcrum than the green is. But the thing that is true is that when I multiply the area of the red times the distance that the red is from the fulcrum, I get the same answer as when I multiply the area of the green times the distance from the green. And that will happen as I move this thing around. You can see that these two numbers will stay the same. Now, line segments are even worse than circles in that they are one-dimensional, so they don't have weight to speak of. But if they did, it would probably be the longer line segment would weigh more. So two line segments that have the same length would weigh the same amount. And just like before, if the fulcrum wasn't in the middle, you would need a longer line. The longer line would have to be closer to the fulcrum to sort of balance it out. And just like the circle, the rule about when they'll balance, they will balance if the length of the red times the distance from the fulcrum to the red is equal to the length of the blue times the distance from the fulcrum to the blue. So if the product of this times this is equal to the product of the red line segment's length times the distance from the fulcrum, under those conditions, those two things will balance. And that's the second thing you have to be aware of. We have the centroid and the law of the lever. And both of those things are, sort of widely known. These next two are much more obscure. The third and fourth theorems are obscure theorems about parabolas. Back in the day, in Archimedes' time, they studied conic sections a lot, and this was really advanced. And after Archimedes, Apollonius wrote a very difficult book about all the properties of conic sections. So let's see what would happen if I take this parabolic segment with this triangle. Remember, point B was kind of like underneath point D, sort of on the line parallel to the axis of symmetry. What if I rotate that like this? And I've recolored it, and I've made it so that this BC line segment has now sort of become horizontal. Now I'm going to draw a couple of lines. One is going to be this line. This is a tangent line through C, so it just touches. If it had the whole parabola, it would just touch that parabola at one point, at point C. Now I'm going to connect D to B and extend it until it hits that tangent line at point E. And then from A, I'm going to draw a line that's parallel to this BD line, and extends it until it hits the tangent line. Move this over a little. And finally, I'm just going to take the segment, not the entire tangent line. So that's an unusual looking triangle, and Archimedes knew some properties of this triangle which are not widely known today. The first property is that in this configuration with all these unusual lines, the tangent line and the parallel line and all that, it will be true that B will always be the midpoint of ED. So ED over BD is going to equal 2. And if I change my original segment, you can see that a lot of things are changing, but what's not changing is that number 2. That will happen if I make the parabola, change the A value. No matter what I do, that ratio is 2. Now, because of that theorem, as a little corollary, this little green triangle, it has the same base as this big triangle. AC is the same base. But its height, that is BD, well, that's half of ED. On the other hand, ED is half of FA. There's some similar triangles here because D is the midpoint of AC. What I want you to know from all that is that this little green triangle is 1/4 the area of the large AFC triangle. So that's a little corollary to this fact. Now, the fourth thing you need to know to be able to understand this proof is the most obscure one of all. If I extend CB and I get to this point K, and then I draw a random point on AC with point O is the random point. And then I draw this line parallel to BD, so I get O, it hits the parabola at P, it hits line KB at N, and it hits FC at M. And that point O doesn't have to go anywhere in particular. So I could move it around. Well, this really obscure theorem says that there is a relationship between these two segments that red segment MO and the orange segment KN, and between these two segments, that blue segment OP and KC, which is sort of a constant thing. And it's definitely not an obvious thing at all, but the relationship is illustrated here. I measured MO and PO. Those are the green and blue. Whoops. I measured MO and PO. MO is the red and PO is the blue. I also measured KC, which is the green, and KN, which is that orange segment. And it turns out that if you take MO over PO, it has a ratio of 4 in this case, although that number doesn't have to be 4, that was a coincidence. And if I take KC over KN, I get a ratio. And it turns out, as you can see here, 1.89, 1.89. No matter where I put O, at least it seems from this sketch, that those ratios are always the same. And they prove this. It's a theorem, very obscure theorem, but it's a theorem that we actually need to follow the proof. So I want you to take my word for it that MO over PO will always equal KC over KN. And then if you cross multiply, you get MO times KN will always be the same thing as PO times KC. Well, those are all the backgrounds we need, those four things to be able to understand the theorem or the proof. Now here's where things get pretty wild. When you have an expression like MO times KN equals PO times KC, that means that has the resemblance of in the law of the lever, that if I take a line segment of length MO and I place it KN away from the fulcrum, and notice here I have MO is this red line, and here's KN, and here on this fulcrum I made KN this orange line, distance from the fulcrum, and I made MO this line here. And on the other side, it equals PO times KC. So that's the green and blue line. PO is this little line. I put that over here, and KC is this kind of long line, and I put it over here on the left. Now when I move the point O around, what you'll see is that line MO sort of gets smaller as it goes through. PO gets bigger, then smaller. Notice how KC, that never changes. That's why I put these blue lines sort of on top of each other, or I made them so their center of gravity was this distance always, whereas the red lines, for those, the center of gravity is different for each one because Kn changes. But Archimedes envisions that geometrical fact as something that's also going to be true about line segments balancing each other out. Well, what happens when I put all the line segments, all the possible blue line segments, and all the possible red line segments together? Well, it starts looking like this. So if each of the lines individually balances out, each red line balances out one blue line, then all the red lines together balance out all these blue lines. So this tear-shaped thing balances out this red triangle. Now a triangle, remember how a triangle's center of gravity is 1/3 the distance on its median? So I'm going to replace the triangle here, or I'm going to fill in the entire triangle. And now, instead of having all the different centers of gravities for each of these vertical lines, I have a single center of gravity at sort of 1/3 the median. Now, this tear-shaped thing is 3 times the distance from the fulcrum as this triangle center. The tear-shaped thing center of gravity is right here at whatever Kc is. But this thing, because of the median, because the centroid is 1/3 of the at the 1/3 point, the center of gravity is only 1/3 the distance. So this tear-shaped thing is 1/3 the weight of this triangle. But those things don't seem very special. But check this out. If I take my line segments and they were to be slanted, this property would still be true because these slanted lines also have their centers of gravity. So now I have this weird tear-shaped thing is the same area as this triangle. You might recognize this red triangle is the same as triangle AFC. And I'm going to do one last thing, which is a little bit cheating, because this blue thing, center of gravity, is definitely at KC. But I'm just going to slide the lines over like this. I'm going to pretend that the center of gravity did not change. But what I want to show you is that the weight of this thing. So maybe you recognize now this blue thing is the parabolic segment. And this is showing that the parabolic segment has 1/3 the weight or area of the red triangle. Now you might remember I mentioned before that this little green triangle here is 1/4 the area of the red triangle. So I could actually replace that red triangle with 4 of those that little triangle. And at this point we could say, something like this: parabolic segment is 1/3 times the 4 triangles. Or if you want, we could say it this way: the parabolic segment is 4/3 triangle ABC, which is exactly what we were setting out to prove. If you like to have things equally balanced on the fulcrum, we could go like this, move this guy over, and then we would need 2 of those parabolic segments because I've moved this twice as far, and I can move it a 3rd time. And now we can see that 4 of those triangles balance out 3 of the parabolic segments. In other words, what Archimedes set out to prove, that the parabolic segment is 4/3 times the area of that inscribed triangle. And it was all based on those 4 theorems, including the 2 pretty obscure ones about parabolic segments and the relationships of the lines in them. Here that is from before, nicely made. You can see segments 7.34 versus 5.51. And as I move this, the areas change, but the thing that does not change is the ratio, 1.33. Of course, nowadays with integral calculus, you could calculate out these areas pretty fast, but this was a great achievement for 250 BC. If you like this proof and you want to learn more about Archimedes, I learned this from a great book called Archimedes, What Did He Do Besides Cry Eureka by Sherman Stein. This book, you can get it for about $15, and it has about 9 or 10 of the treaties in there. It really is an amazing book. There are much more complicated translations of Archimedes and literal translations that are pretty hard to follow. But this book explains it really nicely. Plus, they get into the whole story of how this proof was lost for hundreds of years. The only copy of the method was erased, basically, and then found hundreds of years later. And we were able to get this proof. And there's other proofs in the method, including the volume of a sphere. I made a video about that one that you can check out. My other YouTube videos if you're interested in this kind of stuff. Thanks for watching.